When high volatility events strike the crypto markets, standard user interfaces often become liabilities. The screen floods with flashing indicators and rapid price fluctuations that compete for the user's limited attention. The primary architectural constraint of traditional Web3 platforms is that their presentation layers are rigidly static. They deliver the same high-intensity visual payload to a novice trader as they do to an institutional professional. This lack of differentiation causes significant cognitive fatigue during rapid market moves. When a user is forced to filter unnecessary noise manually, it leads to slower execution and higher rates of platform abandonment. To address this UX bottleneck, the Neuro-Symbolic Adaptive Crypto ecosystem introduces an architecture that monitors and responds to user stress in real time. This system shifts the React-based user interface from a passive tool into a closed-loop control system, allowing the dashboard to regulate its own complexity based on the user's needs. The model operates across three distinct strata: a biometric sensory layer for inputs, a neuro-symbolic kernel for processing, and a cognitive actuation engine for outputs. The bottom layer extracts behavioral telemetry in real time, pulling raw interaction data directly from the browser session. This data moves into the middle layer, where the kernel processes the behavioral streams to generate specific control variables. Finally, the top layer uses those variables to physically alter the layout and movement speed of the interface. By bridging these layers, the dashboard functions as an active partner that dynamically regulates the user's cognitive load during high-stress sessions. To regulate fatigue, the system must first perceive it. It does this natively within the browser, without the need for external webcams or wearable sensors. The collection protocol utilizes raw document object model, or DOM, events to track interaction vectors. The DOM is a programming interface that represents the structure of a web page, allowing scripts to monitor every element a user interacts with. The first vector is frustration sensing. The system tracks rapid, clustered, and repeated click events. The system identifies these rage clicks as a primary indicator that the user is experiencing visual overstimulation. To measure broader navigation efficiency, the system monitors a metric called path entropy. This scatterplot compares a direct, low-entropy path against a tangled, high-entropy one. Highly erratic or non-linear cursor movements are quantified mathematically as a high-entropy state. A high-entropy score signals to the system that the user is lost or overwhelmed by the current density of the UI. The third vector is dwell-time interest mapping, used to establish a hierarchy of user intent. This wireframe demonstrates the system using the native Intersection Observer API. The Intersection Observer is a browser tool that tracks when specific elements are visible to the user, allowing the system to log which asset modules hold the user's attention the longest. By combining frustration hits, path entropy, and dwell time, the system generates a continuous behavioral fingerprint of the user's stress and intent. High-frequency UX adaptation requires zero-latency processing. This makes traditional client-server cloud logic too slow for real-time adjustments. The system relies on edge computing, which means the entire processing kernel runs locally on the user's machine within the browser. Edge computing is a method of processing data at the edge of the network, closest to the user, to eliminate transmission delays. The neuro-symbolic architecture is a bifurcated system designed to handle two fundamentally different types of data: probabilistic human behavior and deterministic financial mathematics. The neural half is a custom feed-forward neural network implemented in JavaScript. A feed-forward network is an AI model where information moves in only one direction, from input to output, allowing for efficient real-time classification. This network ingests the noisy biometric telemetry to calculate a single probabilistic output, the predicted future load score. While human behavior is probabilistic, financial data requires absolute precision. Rigid rules engines are necessary to handle hard calculations. This is the role of the MT4 Advanced Analytics Suite, powered by Ethers.js and direct WebSocket streams. MT4 is an upgraded analytical framework that extends standard trading indicators with deep liquidity and volume tracking tools. This deterministic layer manages mathematical functions like real-time order flow and divergence detection with consistent accuracy. Because both halves of the kernel operate locally, the system maintains a high degree of privacy. Your behavioral telemetry never leaves your device. The Neuro-Symbolic Kernel balances the need to interpret messy human emotion with the necessity of executing deterministic financial math entirely at the edge. Once the variables are computed, the Actuation engine determines how to physically alter the React 19 interface. While traditional animation speeds are usually hard-coded, this system binds CSS transitions and framer motion properties to the kernel's live outputs. This process is called kinetic UI synchronization. The interface motion literally decelerates to create a calming environment during moments of high cognitive stress. As the predicted future load score spikes, the system automatically increases transition durations, visibly slowing down UI motion to prevent further overstimulation. High telemetry spikes can also trigger dynamic theming, swapping a complex glass-style interface for a minimal Zen theme that emphasizes negative space and muted tones. Adjusting speed and color is only part of the solution. To mitigate interface friction, the system must also curate the actual content on the screen. This curation is managed through predictive portfolio sorting. A localized reinforcement learning algorithm uses the dwell time metrics to reorder project cards. Reinforcement learning is a type of machine learning where an agent learns to make decisions by receiving rewards for specific actions, in this case, prioritizing the assets the user values most. Complex execution tools, such as risk-reward simulators, are only deployed when the system detects a highly confident, low-entropy user path. The Actuation engine ensures the front end organizes itself to mitigate overload before the user even consciously recognizes their own stress. Looking at the architecture as a whole, it operates as a continuous, self-correcting cycle. This diagram shows the loop. DOM telemetry informs the Edge AI, which rewrites the UI state, which then alters user behavior to generate new telemetry. This closed loop provides high-performance personalization while maintaining local security, as no personal behavioral data is harvested by a central server. However, a purely local model cannot learn from broader, global market trends. To solve this, the system includes an optional macro-learning layer called the Mothership Telemetry Sync. Local instances can optionally send anonymized behavioral telemetry to a central hub, creating a global dataset of how users interact with the UI during specific market events. The central hub processes this big data to refine the base reinforcement learning models, pushing updated optimization rules back down to every individual user session. The business value of this system is the optimization of the user journey. By tracking intent mathematically, the platform can streamline the path from wallet connection to final execution. Advanced metrics like footprint volumes are only valuable if algorithmic curation ensures the user has the cognitive bandwidth required to interpret them. Dynamic cognitive interfaces offer a method to navigate complex data by partnering with human perception rather than overloading it.